Great. Okay. So hi, everyone. Welcome to lecture A.2. Today, we will continue discussing interactive proofs. And specifically, we will study perhaps one of the most, probably the most important construction of interactive proof, and that is the Sumcheck protocol. It plays an absolutely central role in the theory of interactive proofs. And it's going to be a bit of a technical lecture, but we have exercises ready in during recitations to help you review this material and play with it. All right. So we saw last time an interactive proof for graph non-isomorphism, okay, which is a language that is in CoinP but is not known to be in P. Okay. Yet a GNI, while being outside of P, is not a very expressive problem in the sense that it is not even believed to be CoinP complete. Okay. In fact, it's not only believed, but if so, the polynomial hierarchy would collapse. Okay, this is like some standard result in complexity theory from the 80s. Okay, so in some sense, like the idea of scrambling the graph from yesterday just gave us an interesting interactive proof, but didn't really get us much beyond some trivial examples. We would like to understand how much further we can go. Can we decide much more expressive or powerful problems using interactive proofs? Today we'll see a couple of theorems. The first one is we'll prove that the language unsat, that is the language of unsatisfiable Boolean formulas, has an interactive proof. Now, the same way that sat is NP complete, unsat is co-NP complete. And therefore, by giving an interactive proof for unsat, we drag all of co-NP inside IP, right? So it's basically saying every language in co-NP has an interactive proof, okay? By simply reducing to unsat first using a polynomial time reduction and then running an interactive proof for that language, okay? So this is it's a pretty large chunk of languages, and it takes us already well beyond GNI, okay, where we were before. In fact, basically almost the same proof will take us much farther. We'll show that sharpsat, okay, which is counting the number of satisfying assignments to a Boolean formula, has an interactive proof, okay? Notice that sharpsat has as special cases sat and unsat, right? Because sat is when this number is greater than 0, and unsat is when this number equals 0, okay? But counting exactly number of satisfying assignments, that is the problem sharpsat, okay? And there's a complexity class that goes with it. It's called P to the sharp P, okay? Which, because we have an interactive proof for sharpsat, we will be able to prove that P to the sharp P is in the complexity class IP. And P to the sharp P, what is this complexity class? These are the languages that are decidable in polynomial time via a machine that is given a sharpsat oracle. Okay, so it's just an efficient algorithm that at any moment in time, it can just turn around, ask the oracle, could you please tell me what is the number of assignments of this Boolean formula? The oracle answers and the machine continues computing, and it can do this as many times as it wants until it decides, as long as overall it runs in polynomial time. Now, you may or may not be familiar with complexity class. We won't get into the details. I'll just say that this is like an enormous complexity class, okay? Is way beyond NP and co-NP, okay? This is, in some sense, maybe the picture you should have in mind. Here is P, right? P is contained in NP and co-NP, right? And they intersect in this possibly strict superset of P, which is NP intersect co-NP. And you have something known as the polynomial hierarchy, which is essentially considering satisfiability problems with existential and universal quantifiers in alternation. Okay, so co-NP is for all and NP is exists. But you can also consider exists for all and for all that exists. That's the second level of the hierarchy, sigma 2 and pi 2. And you can keep going. And the union of all these things is polynomial hierarchy. P to the sharp P, even beyond that. Okay, so this is like an enormous amount of problems. For example, in the second level of the hierarchy, there is the circuit minimization problem, where you're deciding whether a given circuit is the smallest circuit that computes a function. Okay, that's an example of a problem that is, say, above NP and co-NP. Okay, and we would have an interactive proof for that. Okay, so these are like pretty, it's pretty powerful result. Now, okay, that's all fun, but you know, we also have to prove these theorems besides stating them. And the point here is that the one example of interactive proof that we saw in the last lecture was pretty tied to the specific structure of graph isomorphisms. It was using this equivalence class relation that you impose on graphs using the isomorphic relation. But it's unclear now that we discuss, let's say, Boolean logic, right? Satisfiability of Boolean formulas. What structure are we going to use? It's not clear there's any natural randomization properties on Boolean formulas, right? So it's kind of really not clear where to start, okay? And not only it's not clear, but somehow there are important new ideas we're gonna have to learn that are going to be recurring themes through this school and in general probabilistic proofs, and that is the idea of arithmetization, okay? Which we'll see shortly, and the Sumcheck protocol, which is the title of today's lecture. So at a very high level, you know, most of these theorems will follow from understanding how to translate problems about Boolean logic to problems about polynomials that are about sums, and then running the Sumcheck protocol, which is an interactive proof for checking the sums of polynomials over certain domains. Okay, and that's like roughly the plan. And basically following that plan will kind of give both theorems almost automatically. All right, so let me now, before I continue, let me see if there are questions in chat. Yeah, so this, I should clarify here that kind of P to the sharp P is, so we need to talk about decision problems, right? And sharp P by itself is a so-called counting class, okay? So it's not like a normal language, okay? And if you want to kind of get a decision question, like this decision language, the typical way to do it is... Excuse me? Can you hear me? I hope you can hear me.
Yeah, we can hear you, we can hear you.
Whoever can't hear me, I'm sorry. But I'm not sorry that other people can hear me. Like, I was getting really stressed. I get sense. I hope you can sort it out on your side. But as long as some people can hear me, like at least they don't have to sweat like yesterday. So, anyways, I won't linger on this too much, but I'll just like point you in the direction that this has to do with the difference between counting classes and sort of decision problems. And the way you move between counting classes and decision problems, you kind of put them, you give a counting oracle to a decision kind of machine, okay? So that's why. But intuitively, you can think about, you know, sharp P is inside IP, even though sharp P, you cannot physically be inside IP. And what does a proof of counting problem entail? We'll see it later. I'll just write down the specific claim that interactive proof will be proving, okay? Roughly speaking, rather than the interactive proof computing the answer, you claim the answer and the interactive proof proves that the answer is correct, okay? So yeah, that's roughly the answer. Okay, so that's the plan for today. It's going to take us, most of the technical meat will be around understanding the Sumcheck protocol, but before I move on, do we have a clear plan for today? Any questions? Okay, so, and I do know you've sort of reviewed the definition of interactive proof in the recitation, so you know that's why we are not doing that here. Great, so let's first talk about arithmetization. So why are we even arithmetizing? This is motivated by the fact that we have good interactive proofs for problems about polynomials. So now this motivates the problem of translating questions about Boolean logic to questions about polynomials. So to remind you, a Boolean formula is a tree, okay, where every leaf node is an input, okay? For example, a variable xi could be x1, x5, x7, And every internal node is a logical operator on its children. So you can have like an OR operator, an AND operator, or you can have an NOT operator, in which case there's a single child. So here's an example of a Boolean formula, right? So you have x1, x or x3, that gives you, this wire over here. You have x3 gets negated and then given as input to an AND gate. And then you take these two outputs and you AND them. That's an example of a Boolean formula. Now, arithmetization is a syntactic transformation that takes a Boolean formula and gives you back basically what's called an arithmetic circuit. You go through this tree and you replace negations with arithmetic expression. You replace Boolean operators with arithmetic expressions. For example, not x will be replaced by 1 minus x. Why 1 minus x? Well, because when x is 0, 1 minus x is 1, which is what you would want to get if you negate 0. And if x is 1, when you get 1 minus 1, you get 0, which is what you want to get if x is 1 when you negate it. And by a similar logic, x and y becomes x times y, where the times is the multiplication of a certain field. And x or y becomes x plus y, where the plus again is addition over a certain field. We'll talk about the field in a moment. But syntactically, what happens is that you turn this Boolean formula into this arithmetic circuit, okay? Which is just an expression that takes inputs and multiplies or adds things over a certain domain, okay? Now, this transformation satisfies certain properties. First, the so-called total degree of the polynomial induced by this one is bounded by the size of the formula. Why? Well, because you start out with your inputs of the polynomial are, degree 1, they're just inputs, right? When you add the things, well, certainly the degree doesn't increase, right? It's at most the maximum of the two inputs, right? When you add two monomials or two polynomials, the total degree of the polynomial, that is the sum of the two input polynomials, will be at most the maximum. When you multiply things, they add up. Whichever way, because this is a tree, right, and inputs like subparts are not reused, it's kind of easy to see that the total degree of the output is at most the size of the formula, okay? Because kind of things are at most additive, okay? And you get at most, in the worst case, you have multiplication everywhere and just degrees add up, okay? They add up to the size of the formula. Also, this is an efficient arithmetic circuit that evaluating it at any given input takes no more than evaluating the original formula, like size of phi operations. And finally, this is the important part. Let's say that the original Boolean formula was a 3CNF with m clauses, just for simplicity. Then, if the formula was unsatisfiable, the sum of this polynomial that we obtained over all Boolean inputs is 0. Why? Because look, anytime we get something 0 that is supposed to be 0, it is propagated as 0, right? So if x and y is 0, then x times y is also 0. If x or y is 0, then x plus y will also be 0, okay? And if not x is 0, then this will also be 0, okay? So on any input, on any Boolean input that would have made the formula be 0, the arithmetic circuit as an expression over some domain will also be 0. And if you sum up a bunch of zeros, you'll get still 0. Conversely, if the formula is not unsatisfiable, namely it is satisfiable by some input, it means that at some point somewhere, this arithmetic expression is going to evaluate to something that is greater than 0. But wait a second, what does it mean greater than 0? Well, let's say that we're working over the integers, okay, for now, okay, as opposed to a field. Then whatever we're going to get here is going to be, if it's not 0, it's going to be 1. If here we have something greater than 0 times something greater than 0, this is still going to be greater than 0. And if we add up two things that are greater than 0, it's still going to be greater than 0, okay? So, but we also know that this quantity that is greater than 0 won't be too large, okay? Because we have at most 2 to the m inputs that we're adding up. So we have at most a 2 to the n, right? So 2 to the n inputs, and we have a multiplier 2 to the n. And any given evaluation in a 3CNF is going to be of size at most 3 to the n. Why?
Sorry,
well,
I have a question.
Yes.
If you don't do, if like when you do an OR, your addition isn't modulo 2, and then you do a NOT, then you're not really going back to 0, are you? I mean, if you do 1 minus x when beforehand you had something that wasn't 1, is that still a NOT?
So we're not over a field of characteristic 2 here. So right now think of the integers, and then we're going to mod a large prime. Okay, this particular arithmetization works only when your characteristic is large enough. Okay, but good question. And I guess we're getting to it just now, why that's the case. So in a 3CNF, you have clauses that look like, I don't know, x1 or x3 or x5, and I don't know, x7 or x2 or I don't know, x1, and so on and so forth, right? When you turn the ors into pluses and the n's into times, okay, that looks like an x, into times, it means that one of these will have size at most 3, right? Because in the worst case, all of the literals are 1. And we have a total of m of them. So we have 3 times 3 times 3 times 3 times 3, right? So it will have size as an integer. There is at most 3 to the m. And down here, so it means that in the worst case, the formula is a so-called tautology, that it is satisfied by every input. Potentially, in the worst case, each of the satisfied inputs will make it a size at most 3 to the m, and we have 2 to the n summands. Okay, so whatever this thing is going to be an integer strictly above 0 and at most 2 to the n times 3 to the m.
Excuse me, I do not understand the part that it's strictly greater than 0, just like the question that I was asked a moment ago.
Okay, great. So,
I mean, I understand the upper bound, but not why it is strictly larger than 0.
Okay, so if, let's take of the 3CNF just because it's easy to understand, okay? Let's say that I am given an input that is satisfiable, okay? So it means that whatever Boolean inputs I have, they will make this clause satisfied, and so on and so forth, right? All I want to claim right now is that I get an integer greater than 0, right? Now, if these are satisfied, it means that at least one of these literals, negated or not, ends up being 1, right? So you will have something plus something plus something, at least one of which is 1. And all the others are, in the worst case, 0, right? So this clause will evaluate to an integer that is greater than 0. Okay? Now that has to be the case for every clause, right? Because the clauses are ended and the whole thing is satisfied. So that's going to be something greater than 0. This is going to be something greater than 0, and so on and so forth. When you multiply them all together, it's going to be something greater than 0. So that's why here I can write greater than 0.
I see, that's right. So this, I'm convinced that this is true for 3CNF. So would that be also true for satisfiable formulas in general?
It's more complicated to understand what happens for general formulas. We'll see a more precise arithmetization in a moment where it's easier. So here I'm not claiming that I don't want to try to claim something for general Boolean formulas. We won't even need that necessarily, okay? There is a slightly more precise arithmetization we'll see in a couple of slides where it's pretty easy to see what happens for all formulas. This is a pretty coarse type of arithmetization because of there's a comment in chat that is pointing out why is the or this way as opposed to some other expression. We'll see later what that helps us with. For now, let's just focus on 3CNFs. Okay. If I had to guess, I think that this limitaization does not have this property for general formulas. It only has it for 3CNFs. But we don't need to care about that right now.
I have a question as well. So this upper bound, this is strictly greater than, right? Or strictly less than 2 to the n times 3 to the m.
It could be as large as this, right? Because I could have a 3 here, a 3 here, a 3 here, and they will all add up.
Yeah, but but then you'll have some assignment of the AI. You can't just have that every single assignment has 3 everywhere. That doesn't seem possible to me.
Sure. Yeah, I agree. Though we won't need that. But I agree.
Okay.
I agree. Or at least I don't see how to write down a formula where every single one will achieve that 3 to the m.
Yeah.
I agree. Now, what we learned from this is that we can fix a prime q to be greater than, or at least if we use the strictly less than suggested by Felipe. So a prime large enough such that the formula is unsatisfiable if and only if this sum of this polynomial over the so-called Boolean hypercube is 0 modulo q. Okay? So I pick the prime large enough so that there are no overflows, and I'm precisely capturing when it is 0. Okay? All right. So that's kind of all I wanted to say for this slide. Let me just see if there's I think I answered all the questions also in chat. But all we've done so far is to take this unsatisfiability problem and turn it into a question about sums of a polynomial. Okay, a polynomial that we can evaluate at any point and doesn't have too large of a degree. Okay. Any questions about this slide? All right, so there's a question by Yotam. So I don't know if exactly. So in I think Tal gave the right answer that we are currently considering 3 CNFs, not general expressions. So the expression you wrote down, if anything, maybe is a counterexample that shows that this property doesn't hold for general formulas. Right now, we're doing it just for 3 CNFs. We'll see something an arithmetization later that does hold for general formulas. Here, we only care about what happens for 3 CNF. Any further questions for this slide? Oh, yeah, there's a question by Guy. Why is there multiplication here rather than an addition? Because we are summing 2 to the n things, and any one of them have size at most 3 to the m, right? So if you do 3 to the m plus 3 to the m plus 3 to the m, and all of this you do it 2 to the n times, then you're going to get 2 to the n times 3 to the m. Okay, great. Further questions about this slide? Great. Okay. So what I'm going to do with this? Now we have this kind of pretty clean problem. Is basically what is the sum of a polynomial over an exponential size domain, a domain of size 2 to the n, right? And this takes us to the Sumcheck protocol, which is precisely an interactive proof for statements of this sort. Okay, we have some domain. Maybe it's not 0, 1 to the n. Maybe it's h to the n for some h. Okay. And we are given some polynomial, and the prover claims, look, the polynomial p summed over h to the n has value gamma. Okay. Now, in principle, the verifier could just say, well, don't help me. I will check it myself. It evaluates p everywhere on h to the n. But that is a pretty large domain, right? And it will take the verifier exponential time potentially, right? Like before, the verifier could have just checked that the formula is not satisfiable on every possible Boolean input, okay? But that wouldn't be an efficient thing. Instead, we'll see an interactive proof where the verifier, rather than, let's say, working in effort poly in h to the n, it will pay in something like poly in h and n, roughly, okay? So it's like an exponential saving. It will be polynomial in, you can think about it, the side of this hypercube and the dimension of this hypercube. All right. So let's just get into it. this is a protocol that is has reasonably intuitive to describe, but is still pretty clever. And so we'll just talk about it. Okay. So the prover receives as input whatever field we're working on. For example, in the case of the previous slide, we'll be working over the prime field FQ for Q large enough. But in general, you just have some field. The verifier also knows the same field. Both are given as input to the H that we're talking about, the number of dimensions, the claimed sum, and the verifier will have just for now oracle access to the polynomial. Okay, so in some sense, it will barely have to touch the polynomial that we're summing. So this denotes the verifier will just make a small number. In fact, it will turn out to be one query to the polynomial in order to check this claim. Of course, the prover will have to manipulate the polynomial in more non-trivial ways, so we just give it as an explicit input. So the Sumcheck protocol is in this case, n-round protocol, where n is the number of dimensions or variables, where the verifier keeps sending random coins at every round, and it works roughly like this. In the first round, the prover will compute a partial sum. What is a partial sum? It will say it will sum over all the dimensions, let's say, but the first one. Okay, we call this polynomial P1. It's the sum of P over h to the n, but for the first dimension. So really over h to the n minus 1. That is a univariate polynomial whose degree is not too large if the total degree of P is not too large. And it just tells the verifier, I claim this is the partial sum of the polynomial P over h to the n. There's a question about, what is h? I'll write here, e.g., h, for example, could be 0, 1, or whatever it is. In the previous slide, we were summing over 0, 1 to the n, but in general, the Sumcheck protocol works over anything that is h to the n. Okay? So any kind of, you can think about it as a product set. And it doesn't even have to be the same h. You can have h1 times h2 times h3, all the way up. It has to be something that is rectangular looking. So in the first message from the prover to the verifier will be this partial sum. And the verifier receives it. For all it knows, the verifier, this is just garbage. So it could just go ahead and check it, right? So there's a natural first check, which is to say, look, if you claim this is the partial sum of everything but summing over the first coordinate, let me just check that. I will sum this polynomial over alpha 1 over h, and I should get gamma. Okay, so this is like a natural consistency check on this partial sum. All right. But of course, the prover may have sent some polynomial that is not the correct partial sum. It just so happens to sum up to gamma when you sum it. So the verifier has to do further investigation. Is this the correct partial sum for the first one? Okay. So what the verifier does, it will sample a random point, omega 1, send it to the prover. Okay. And the prover will now be required to send the next partial sum, having fixed the first coordinate to omega 1. Okay. So this randomness that is sent by the verifier, the prover fixes the first coordinate and it sums over everything but the second coordinate. This gets P2. Okay. The prover sends it. And again, for all the verifier knows, the prover could have sent garbage. Maybe P2 is just like nothing. So it's nothing interesting. But there is a natural consistency check it can do. It can check whether summing over the free variable, you get the previous polynomial precisely at omega 1. Okay, this is the natural consistency check for the polynomial P2. But again, maybe the prover sent just not the right P2, just something that happens to sum up to P1 omega, P1 at omega 1, and maybe has nothing to do with the original polynomial P, right? So the verifier keeps basically probing the prover with further randomness until at some point it gets to the end. And the prover is supposed to send the polynomial P evaluated at omega 1, omega 2, omega 3, blah, 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 all the way up to omega n minus 1, but for the last coordinate x, and it sends it. There is a natural consistency check. And now, finally, the verifier can just check by sampling the last variable that this last polynomial that was sent Pn, evaluated at omega n, truly is the original polynomial evaluated at omega 1, omega 2, all the way up to omega n. Okay, so this is the one time the verifier actually has to query P. Okay, it only has to access it at a random point, the point omega 1 through omega n. Okay, so you can think of the Sumcheck protocol as being hooked to the claim at the beginning and at the end. At the beginning, you have this consistency check relative to the claim sum, and at the end, you have this consistency check connected to the actual polynomial, and in between, you have these checks that are connecting the intermediate polynomials that are helping you reach one to the other. Okay. Okay, I will talk about the protocol further in a moment. Let me see what the questions are happening in the chat. All right, so a couple of questions. Why are these points sampled from the whole field rather than H? Well, we'll see in the analysis of soundness that it is important that the domain from which the randomness is sampled is large enough. Okay, so we cannot afford just to sample them necessarily from H. Okay, so there's going to be some errors that accumulate, and we're going to need the domain from which we sample to be large enough. Doesn't have to be F, just has to be like some challenge set that is large enough. For example, the simplest challenge set to consider is the whole field. Okay, so we'll come back to that in analysis. There's another question about what is the representation of the polynomial that is sent. It doesn't really matter too much. You can send it in the coefficients. You can send it as evaluations. Whichever representation, the verifier will then take it and will have to perform this consistency check. I'll mention that actually the Sumcheck protocol is used in practice, and using one or the other representation of polynomials affects like sort of surrounding protocols. So sometimes you pick one, sometimes you pick the other. For right now, it doesn't matter. These are interchangeable because going from evaluation to polynomial coefficients is these are efficient operations that the verifier can do itself.
I have a short question. So what's the reason why we give the verifier oracle access to the polynomial rather than just give it to him?
It is to highlight, so the question was, why do we give the verifier oracle access to the polynomial rather than to giving it, is to highlight the fact that the verifier barely has to manipulate it. The only reason it needs the access to the polynomial is to evaluate it at a random point. And this property of Sumcheck is important in a number of applications that, for example, we'll see, I think, in the next lecture. No, next lecture, where it's important that you don't need to have the polynomial, you just need to be able to kind of query it at a random point, okay? So here we're highlighting that the only way the polynomial participates in the verifier's decision is being queried at a random point, the random point that's defined by the verifier's randomness. This last message is primarily for syntactic symmetry. So you have one round, another round, but you don't really need to send it. By the time the prover sends the last polynomial, he can go away. This is primarily for syntactic symmetry. So there's a good question by Amit. So we're assuming that we can evaluate the polynomial at a non-Boolean input. That is the whole point of arithmetizing a Boolean formula into a polynomial, that we can evaluate it on non-Boolean inputs. That is exactly the power of arithmetization. We encode Boolean objects into non-Boolean objects, algebraic objects, and then these algebraic objects, we can evaluate and manipulate them in ways that are not Boolean, okay? This is precisely what we're going to leverage, okay? I think I've addressed all the chat questions. Let me remark some aspects about this protocol, and then we'll take some more questions. Notice that the communication transcript that is sent is not that large. We have n messages, and how large is each polynomial, where it's going to be at most the individual degree of the polynomial p, right? In multivariate polynomials, you have individual degree or total degree. Individual degree means like what's the highest degree in any variable, and total degree is like add those up, right? Here is at most n times the individual degree that we're sending. This is, of course, just one field element. So this is at most the number of field elements that we're sending. So it's like n times the individual degree. It's not like something to the n, right? And the verifier is also efficient because it is doing n checks. Each of them is a sum over h things. and each of them is evaluating a polynomial, univariate polynomial, whose degree is the individual degree of P. Okay, so it's roughly this many field operations plus, one evaluation of the polynomial P, which might take, if the oracle is realized in some way, might have its own cost. Any questions about the syntax of the protocol? We'll talk about the analysis, quite extensively over the next few slides, but is there something unclear syntactically about what's happening here?
Ale, just a question.
Yeah.
In the previous example, P was multilinear, right? Because we used every variable only once.
In the previous, it is actually not multilinear because you have, let's put it like this, let me go back to, there we go. Or maybe I should have, there we go. So here, if the same variable appears in multiple clauses, which it will, okay?
But your definition of a Boolean formula was that you use every variable only once because it is a tree-like, right?
I should have been more precise. Sorry about that. The variables can appear multiple times in the leaves, okay? So, for example, here you see that x3 appears twice. That is fine, right? And this is analogous to what happens, for example, here x3 can appear in two places, right? So the whole point of the difference between a Boolean formula and a Boolean circuit is that in a Boolean circuit, you can reuse the subcomputations, but in a Boolean formula, you can't, okay? So a Boolean formula is a tree, but when you populate the leaves, of course, you can put the same input in multiple places. It's just that once you start computing up, things have to be like according to the tree, okay? You cannot have, I don't know, this thing being reused somewhere else, okay? But when you lay out the inputs at the leaves of the Boolean formula, it's okay to reuse the same input multiple times, okay? And this is indeed here in this example. Hopefully that clarifies it. And because of that, it will not going to be multilinear. And more generally, so three sat, we don't know that it is NP complete with each variable appearing once, though we know how to make it go down to maybe like 2 times, I think, each variable appearing twice, right? Using by replacing variables and adding clauses, right? But NP completeness of a 3CNF at best, we know how to make it down to each variable appearing twice.
I have a question.
Yeah.
What does it intuitively mean to evaluate a Boolean formula at a non-Boolean input? Like intuitively, are we getting more out of by evaluating at these special field elements? It seems somehow we are evaluating a combination of many Boolean formulas at once instead of just evaluating it at a single Boolean point.
Well, first, syntactically, I hope it's clear, right? We arithmetize the formula and then we get a polynomial. We evaluate an arithmetic circuit, we can do whatever we want, right? Now, intuitively, what's happening is that underneath there is some implicit code, okay? We are using some polynomial code to basically sample some random point of this code outside of the systematic domain in order to gain distance, okay? So we're kind of encoding, like you can think about the evaluation table of this formula becoming like a much bigger evaluation table through this encoding that has distance, okay? From, this formula or a different formula, okay? That's intuitively, we're encoding, and therefore we have redundant information that we have access to. The non-Boolean evaluations are this like extra pieces of information that we're attaching onto the message. This is intuitive, and formally, we'll see how it is sort of necessary to have many points to evaluate from in order to get any soundness in this protocol. Hopefully that answers a bit that question.
Yeah, thanks.
Further questions about Yeah, also there's a good point by Felipe that says if every variable were to appear only once, then we could just set it to be the right value and then go home. So that likely means that you cannot expect it to be NP complete. Further questions about this slide? Great. So let's move on. Now, the clear part here is that in explaining the protocol, I already convinced you of the perfect completeness of this protocol, that if the statement is true and the prover follows the prescribed instructions, then this check will work, this check will work, this check will work, this check will work, whichever points are sampled by the verifier, which means that the verifier will accept it with probability 1. Okay? We kind of designed the protocol to work out, right? So this part, it's easy, right? Less clear is soundness, okay? So what we're going to prove is that if the claim is not true, then whatever strategy the prover employs, the probability the verifier accepts is bounded from above by n times the individual degree of the polynomial divided by the field. And more generally, if you're sampling from some challenge set, you could write here size of the challenge set, okay? If you're sampling from some challenge set. And we'll see later why that's the case.
So
yeah.
Another question. So when you say the individual degree of P, you just mean the highest power of some variable appearing in the polynomial?
Yeah, exactly. So you can think of the polynomial is a formal sum of monomials with coefficients, right? In each of those monomials, the variable will appear. And then to compute the individual degree, you just say, okay, x1, what's the highest degree that appears in any monomial? I don't know, it's maybe 5. Okay, well, individual degree is at least 5. But maybe x2 appears with a degree 10 in some monomial. So the individual degree actually is 10 if indeed no other variable exceeds that, right? So just the highest degree of any variable. Intuitively, why? Well, because, that's because we're kind of slicing up the polynomial by variable, right? First, we experience the first variable, then we see the second variable alone, then we see the kind of the final variable alone, right? So we're only see this kind of orthogonal degrees, right?
1 and Pn are all bounded by the individual degree of the original polynomial.
Excuse me?
All the PIs are bounded, the degree of all the PIs is bounded by this individual degree of the original P.
Correct, exactly. So that's why it appears in the expression. And they are the ones that participate in the consistency checks, which ultimately determine soundness, right? So this is expression. That's a pretty it's a pretty simple expression. And in fact, it can be improved slightly. I forget if it's in the worksheet or not, but you can slightly improve the upper bound to be something that is more accurate. This is like an upper bound itself on this expression. So over the next, I guess, 10 minutes or so, we're going to prove this claim, okay? So now it's soundness, so we have to consider every possible strategy the prover could do. So, okay, fix some arbitrary malicious prover. Now, what does the malicious prover do? Well, it defines some choice of polynomial per round. Let's call them P1 tilde, P2 tilde, Pn tilde, and so on and so forth, right? The tilde here is a modifier, typographical modifier that is often used for malicious kind of objects, okay? And each of these will depend on the randomness so far. So P1 will depend on nothing, P2 will depend on omega 1. In general, Pi tilde will depend on omega 1 through omega I minus 1, okay? So the malicious prover is fully specified by kind of these n functions on the randomness so far. We're going to define an event, okay? We're going to find n events where EI is the event that in round I, the prover sends the polynomial that the honest prover would have sent. And we say, wait, what do you mean the honest prover? We are in a malicious case. Well, even for even for a false claim, you can still run the honest prover strategy. It will send some polynomial, call that polynomial PI, okay? What is that polynomial? It is the honest partial sum relative to the randomness so far, okay? So the event, EI, denotes the basically event that the prover in that round behaved, like sent the correct partial sum, even though sending the correct partial sum doesn't mean the verifier will accept, okay? It just means syntactically it did send the correct partial sum, okay? And W, it's gonna be the verifier accepts, okay? W stands for the prover wins, okay? So we're gonna prove a lemma, okay? That's gonna be in the next slide. This is kind of a general expression that for any J, the probability that the verifier accepts or that the prover wins is bounded from above by n minus j plus 1 times the individual degree over f plus this expression, which is the probability that the prover wins given that it sent the correct polynomial from round j onwards, okay? All right, this is like a messy expression, doesn't matter right now, we'll prove it in a moment. What I want to do right now is convince you that this expression suffices to establish the claim, okay? So take this lemma and fix j to be equals 1. So what we get when j equals 1, here we just get n, right? And over here, we get the probability that the prover wins given that in every single round, it sent the correct partial sum. Well, this is actually the probability that it wins given this is the case 0. And the reason is that this event is at most the probability that the prover wins when he sends the first one, the first polynomial to be the correct partial sum, because if it does send P1 tilde to equal to be P1, well, the correct partial sum equals to the correct sum. And we know the correct sum is not gamma, period, independent of any randomness, okay? So this lemma easily implies what we want to prove, all right? So all we're left to do is to just prove it. And we're gonna prove it, guess what, by induction, okay? Any questions about this, this slide? All we've done is to set up notation, define some events, state a technical lemma that we haven't proved, and then derive the claim from the lemma, okay? I hope everybody understood why this probability is 0. Right? So if the prover sends the correct partial sum in every round, in particular, it sends it for the first round, and that's a stupid prover, because if you send the correct partial sum in the first round, the verifier will reject always, because when the verifier runs the first check, which is to check whether when you sum up over H, you get gamma, well, what you're going to get is the correct sum, but the correct sum is not gamma. And so the verifier, the prover just shot itself in the foot, right? Okay, great. So somehow, like the whole thing of the Sumcheck protocol is just arguing this point here. Okay. So let's do that. So I copied here the lemma, literally copied, not even rewrote. And the proof is by induction on J. So let's start at the end of the protocol. That's actually the way, like this is in some sense one of the counterintuitive aspects of analyzing the Sumcheck protocol is you start at the end. Okay, you don't start analyzing it from the top, you start analyzing it from the bottom. Okay, so let's say that we are in the last round and the prover, in order to win, it either sent the incorrect partial sum or it sent the correct partial sum in the last round, right? Now, if it sent, so this is saying that this is saying that the probability the verifier accepts sending the incorrect partial sum, right? So let's start opening it up. If the verifier accepts, it means that the last check did go through, right? In the last check, the prover was checking. Let's kind of go back to the Sumcheck protocol to see what happens at the very end. At the very end, the verifier checks whether the final polynomial evaluated at omega n really equals the correct polynomial evaluated at all those random points. Okay? So this is the check that is relevant for j equals 1, so j equals n now, right? So the verifier accepting means that at minimum, the last check passed, right? At minimum. And we are given that the prover sent the incorrect partial sum, like not the correct partial sum. But look, the definition of Pn was like the honest Pn of x was P of omega 1 up to omega n minus 1, comma x. So Pn at omega n is P of omega 1 through omega n, right? So that means that by the definition of Pn, we have that. And now we're asking, we have two polynomials, they are different. We evaluate them at a random point and we're asking, do they agree? Well, this is at most this quantity by something known as the polynomial identity lemma, okay? The probability that a non-zero polynomial, oh, I didn't write non-zero, I should fix that. The probability that a non-zero polynomial vanishes at a random point is at most its degree divided by wherever the point comes from. Why? Because a polynomial has at most its degree many roots, okay? And that's it, that's all the places where it can vanish, okay? So here we are asking, we have two polynomials that are distinct. That means that we have the non-zero polynomial Pn tilde minus Pn, that is a non-zero polynomial, and we're asking when the polynomial Pn tilde minus Pn vanishes at a random point omega n, right? By this polynomial identity lemma, this is at most the degree of the polynomial, which is the individual degree of P, divided by wherever the challenge was coming from, in this case, the whole field, okay? Size of the field. So this is just this term over here. Are we fine with it? So I'm going like extra slow because like, you know, it's not too deep what I'm saying, but these are properties that we'll be glossing over many other times. Sorry, go ahead.
How do you know that the degree of Pn tilde is not larger than the degree of P?
Because if the prover sends a camel, then we reject. In other words, we expect a polynomial of a certain degree, and if because that's how the protocol is described, right? And if we get some different degree, we know the prover is up to something no good, and we just reject, right? So syntactically, we know that the degree of Pn tilde is the same as the correct degree that it should be, but we don't necessarily know whether it is the right polynomial, right?
So is the degree encoded within the encoding of the polynomial, or is that something that? Yeah,
like for example, if the prover was supposed to send me a degree 5 polynomial, and he's supposed to send me the 6 coefficients of that, well, you know, I will receive in the mail 6 coefficients. If I open the mailbox and I find a camel inside, then, you know, it's not 6 coefficients. Yep. I'll reject, right? Mm-hmm. Good question.
How does the verifier know what the degree of the polynomial should be?
It is given as an input, and I should have written it as explicitly in the inputs. Maybe let me go back to over here. There should be another explicit input. Let's say D. I will add it to the slides. I don't know how it got outside. There should be another explicit input D that is a bound on the individual degree of P. And now the verifier does have it, and you just got a bug in my slides. Sorry about that. Good question. Let me just make a note.
Is the bound sufficient, or do we need like individual degree of all the variables?
In principle, you could have different individual degrees for each variable, but this is rarely used. But in principle, you could say, well, I have different individual degree for variable 1, variable 2, variable 3, and you use those different degrees to kind of syntactically check each round's message. And in that world, your soundness analysis will take that into account. And rather than having an expression that is n times that, you might have an expression that is more like sum of I equals going to n and di, right? Something like that, where di is the bound on the ith individual degree, right? Good question.
Yeah, but I was asking even like not from the point of view of a tighter analysis, but if you just assume that the verifier is given a bound on the individual degree, then the polynomials which come earlier, which are less than that bound in the individual degree, might not satisfy this low degree test that you're doing.
So I can't hear you very well, but I think you were asking a question about, is it okay to have like a larger bound even though we don't maybe we don't meet it? That's okay, right? Because maybe some of the higher coefficients are 0 anyways for reasons that are even in the honest case, right? So all we care about right now is what is allowed to be sent by a dishonest prover, right? Because against the dishonest prover, we'll be checking the polynomials agreeing at a random point on that degree, right? So you will basically, your soundness analysis, your soundness error will depend on what is the syntactic bound that the verifier will enforce on its messages, right?
Okay.
Because there is a malicious prover that will take advantage up to that bound, okay?
Mm-hmm. Yeah.
And you have to account for that malicious prover in your analysis, and it means that the soundness error is up to that. So there is a question, why is this called the polynomial identity lemma rather than Schwarzschild lemma? Schwarzschild sometimes sounds scary. Also, there is, I don't know, like if you look into the history, there's actually like many more people that needs to be credited for it. And so, I don't know, usually I just try to have a more descriptive, and this is a name that is also suggested in some papers as something a bit more descriptive and less sort of explicit about crediting some people and not others. But it's completely used to be also called the Schwarzschild lemma. This is the Schwarzschild lemma for univariate polynomials, right? Usually also the Schwarzschild lemma is more about multivariate polynomials, where you kind of build it up by induction. All this is saying is that polynomials don't have too many degrees. I mean, univariate polynomials don't have too many roots. Good questions. Great. Okay, so this was just the base case. Okay. The inductive case is actually pretty simple. Like we're kind of almost home here. We're gonna assume that we're somewhere in the inductive case. So we have proved the claim for n-1 up to 2, right? For j, which is in this interval, and we want to prove it for j-1. Okay. So first, we're going to kind of split up this event, which is analogous to what was happening here, right? So here we were taking this winning event and we split it up into this one and that one, right? So here, in order to make progress, we have to take this event here and split it up, right? So it means that we have the two ej-1, not ej-1 and ej-1, right? All the other ones are the same, right? These guys are the same. And what we want to argue is that this first expression here is at most the very same expression that we had before. And again, it's like a similar argument, okay? So what is the probability that the prover convinces the verifier, given that in the j-1th round, the prover sent the incorrect partial sum? Well, okay, if the prover wins, it means that at minimum, it must have passed the check in round j-1. This is the check in that round. And we're assuming that it sent the incorrect partial sum, but crucially, in the next round, it did send the correct partial sum, okay? So that's why we're using the fact that there's EJ here. And because of that, because in the next round it sent the correct partial sum, we can infer that the sum of pj tilde is the same as the sum of pj, okay? So that's where we're using it there. And then all we're saying here is that because this was the correct partial sum, the sum of pj over h is just pj-1 at omega j-1, this one over here. And now again, we're comparing two distinct polynomials at a random point, which is at most their degree, which is the individual degree of D over F, okay? Now, crucially, like notice that why these are two polynomials evaluated at a random point, because the prover first sends pj minus 1 tilde, and then it sees omega j minus 1, right? So we're implicitly using here the fact that there is an order to the messages, of course, right? That's why there are rounds, right? And the prover first sends pj minus 1 tilde, then it sees omega j minus 1. That is why we can invoke the polynomial identity lemma, okay? And if we go back to kind of the description of the Sumcheck protocol, you're going to see that, right? First you send P1, then you see omega 1, then you send P2, and then you see omega 2, right? That's why I was drawing it in this kind of symmetric way, so that you kind of have this vision of like, that's one round, that's another round, and this is another round, right? Send the polynomial, then see the randomness, okay? So it is independent of it. Okay, so we kind of got till the end of the analysis. We're not always going to be so precise, but you know, for the first analysis of the Sumcheck protocol, we decided to, I mean, it makes sense to kind of write it out explicitly so that you can really follow every step. So there's a question about, can we improve rather than a factor of n by putting a maximum? In general, no, because like if you think about it, like at every round, you have a chance of switching to another polynomial and fooling the verifier, and that's a chance that you have in every possible round. So intuitively, you do expect like things to add up. Now, specifically commenting on your suggestion, that may be a little bit, I may not be able to explicitly parse your suggestion and see where it doesn't work in the proof, but I want to say at intuitive level, in the Sumcheck protocol, you really have an error arising from each round. Intuitively, it is because at every round, you could get lucky by matching up roots of distinct polynomials in any given round. It could happen in this round, it could happen in the next round, and so overall, you could get it. What you can do, though, is to tighten up the analysis to be this one, right? This expression over up here, right? That says that you win precisely when you don't get caught at every single round, okay? And this is like not getting caught at every single round. So I think this is, I'm pretty sure you can design a strategy that matches this bound over here, okay? Maybe that's an interesting, maybe it could be an interesting exercise to see, to write down a strategy that achieves this upper bound, okay? All right, so there's a question about repeat the last transition. I presume this transition over here. So what's happening here is that we have the incorrect partial sum at round j minus 1 and the correct partial sum at round j, okay? Okay, so I guess, no, the last of the blue ones. All right, so I guess this transition here. So this transition here is the following. Pj is the honest partial sum evaluated on omega j minus 1. So when you sum up Pj over h, you will get the valuation of Pj minus 1 at omega j minus 1, all right? And once you do that, now we are comparing two polynomials that are distinct, Pj minus 1 tilde and Pj minus 1, at the random point omega j minus 1. And therefore, that's why you get this expression. And why did we drop the conditioning? Because we used it. We used this conditioning to imply this, okay? We can keep it around if we want. It doesn't, I mean, he was doing an upper bound here. So this is not an equality. Our conditional probability is correct. Condition on the eyes. So I'm pretty confident about the conditional probabilities right now, but maybe we can come back to that at the end of the lecture for these precise questions where maybe I'm gonna get confused longer than I want to. But Michael, please ask me that question again at the end of the lecture. All right. So this is the analysis of Sumcheck. hopefully, going through it in detail in lecture will help you kind of, I definitely encourage everybody to kind of work it out offline and see if you're convinced. Now that we have this last expression, we add this up here and we have proved it for j-1, right? Because we add this up here and it means that we have one more term. So instead of minus j-1, right? And that is what we wanted to prove. Now that we have the Sumcheck protocol, we need to come back and say, okay, well, let's tie it back and combine arithmetization and Sumcheck together for a protocol for unsatisfiability. So here we have an interactive proof where the prover and verifier receive a Boolean formula. And the prover wants to convince the verifier that the formula is not satisfiable. The prover will send an integer to the verifier, and the verifier will check that it is large enough, but not too large. Not too large in a sense that it needs to be able to do arithmetic over the prime field defined by it. And it will check that it is prime. It doesn't even have to do it indeterministically. It's fine even to have like a high confidence randomized primality test, okay? This defines the field of Q. And they're going to arithmetize, both of them, they're going to arithmetize the Boolean formula phi into the polynomial P over the finite field of Q. And then they're going to run the Sumcheck protocol as a subroutine for the claim that this polynomial sums to 0 over the Boolean hypercube. Okay? So the gamma is 0, h is 0, 1, the dimension is n, where n is the number of variables of the formula. And at some point, at the end of the Sumcheck protocol, the verifier is going to want to query the polynomial P. Now, the outer verifier, the one that is running the Sumcheck verifier as a subroutine, knows how to answer the question. It just evaluates P, which is an easy to evaluate arithmetic circuit. And it will evaluate it at this point in the field, omega 1 through omega n. And it can do it efficiently because that circuit is not too large. It's the size of the formula. It gives back the answer, and that's it. Now, the soundness error is going to be n times the individual degree divided by q. Well, n is individual degree. I mean, n is the number of variables. Now, the individual degree of this 3CNF is at most its total degree, right? So I'm being very rough here. And the total degree is at most m, because if you remember, we had m clauses. Inside each clause, it was something plus something plus something. So we had total degree 1. So we have total degree 1 times something on total degree 1 times something on total degree 1. So they all add up and you get n times m. All right. Q is at least 2 to the n times 3 to the m. Well, this is certainly at most a half. Okay. In fact, it's going to be probably much less than a half. So there we go. We have an interactive proof that has roughly n rounds for proving that an n variable Boolean formula is not satisfiable. Okay. We translated the formula into a question about polynomials and we ran the Sumcheck protocol. Okay. All right. So there's a question, can't the verifier choose the Q itself and send it to the prover? Yeah, it can. The reason why I let the prover do it, I was highlighting that there is no specific distribution that Q needs to be sampled from. So we can actually trust the prover, or at least we don't care if the prover tries to pick the prime in some weird ways, as long as it is, within some range. Sometimes it's important that primes are sampled according to some distribution for other reasons. So I like thinking of it as let's let the prover do the searching, and we'll just check that it's prime. That seems that it will save the verifier work.
One question: what is the fourth parameter in the Sumcheck verifier?
Excuse me?
What is the fourth parameter in the Sumcheck verifier? There is a 0.
That is the gamma. Parameter. That is the claimed sum. So this is the gamma.
Oh, okay.
Good question. And 0, 1 is the h, right? So that was the h, right? Okay, so this is like a pretty cute, simple protocol for unsat. Any questions?
Does this work for general Boolean formula or just 3CNF? Oh, it says 3CNF at the top. Sorry, never mind.
Yeah. So I highlighted 3CNF because the 3CNF guarantee is used by the arithmetization guarantee. Great. Okay. So onwards. So let's say that we want to talk about sharp SAT. Now, the arithmetization that we used for unsat was rather coarse in the sense that for every Boolean input, yeah, we did know that if the Boolean formula was 0, then the polynomial at that input would get 0. But all we knew, if the Boolean formula was satisfied by this Boolean input, is that the corresponding polynomial will give me some positive value that is at most 3 to the n. That's not very helpful. We can modify the arithmetization to be more precise, to basically be almost the same, but in x or y, we say x plus y minus x times y. Why this extra thing? Because we basically are keeping the Booleanity. Essentially, this expression and this expression agree on every possible Boolean input. If you have x or 0 or 0, you will have 0 plus 0 minus 0. Okay, that's still 0. If we have 1 or 0, you should get a 1, right? That means you get 1 plus 0 minus 0 times 1, or 1 times 0, still a 1. And if you get 1 or 1, you should get a 1. Well, that is 1 plus 1, that's 2, minus 1 times 1, that's still 1. Okay? And even if we have our characteristic 2, you will get 1 plus 1, that's 2, that's a 0, minus 1 times 1, which is minus 1, which is still 1. Okay? So now we have a new arithmetization that says that on every Boolean input, basically the polynomial exactly follows the value of the Boolean formula. And this is something that we call a low degree extension. Okay? It means that the polynomial evaluates exactly on the values of the formula on the Boolean hypercube. It agrees with it. Okay? So it kind of has the actual function encoded in it on that domain. All right? We'll come back to low degree extensions in a couple of lectures. They play a big role in this course. Before, it was an arithmetization that was not a low degree extension. This arithmetization is a low degree extension. And we can now reduce sharpsat to a Sumcheck problem because for every prime q that is greater than 2 to the n, the number of satisfying assignments of the formula phi is c if and only if the sum of this polynomial is c modulo q, right? Why the q has to be large enough? Because in the event that the formula is satisfiable on every input, the sum is going to be 2 to the n, and we don't want it to overflow. So we need q to be strictly greater than 2 to the n. Okay. So now we have translated this counting problem into a Sumcheck problem. Okay. Well, we know what to do, right? So now if we want an interactive proof for sharpsat, it's going to be as follows. The prover claims that the number of satisfying assignments of the Boolean formula is c. Okay. Well, the prover sends q, the verifier checks that it is in some reasonable range, still not too large and large enough for the arithmetization to work, has to check that it's a prime. It does this new arithmetization. I put it superscript sharp, just to denote it's the slightly different arithmetization. And then it runs the Sumcheck protocol where now the gamma is not 0, but is c, which I even forgot to provide as input to both of them. So the gamma is c rather than being 0. Okay? And at some point, the Sumcheck verifier will want to query the polynomial at this random point, but it can do it, right? You arithmetize the Boolean formula, you have the arithmetic circuit, you just evaluate it, and you return the answer. Okay? So this is how you can have an interactive proof for claiming the correct number of satisfying assignments of a Boolean formula. Now to get p to the sharp p, it's one layer up, right? So a language is in p to the sharp p if you have a machine that decides language given a sharp p oracle, okay? So now we need to have an interactive proof that uses as a subroutine this interactive proof whenever it is needed. So here's a new interactive proof for the language L. You simulated the machine on input X, and whenever the machine wants to make a sharpsat oracle call, it tells the prover, hey prover, I want to make this call to the oracle. Please tell me what is the claimed value. the prover says, okay, sure, the value is this one. And then we engage into an interactive proof for this claim, this one over here, right? And we do it for as many times as this machine cares about, okay? And we just do it. There's one asterisk here that because you're doing this many times, some number n of Oracle calls, you need to make sure that the error of each call is small enough so that you can afford the error in total. So you need to make sure that the error is, let's say, order of 1 over n. Sorry, it should be 1 over n. Just make a note. So you need to pick the q to be large enough so that the expression over here, which is n times the individual degree, which now is 3m rather than m, over q is at most, let's say, half times 1 over n. Alternatively, you can pick the q to be slightly smaller and you just repeat the interactive proof a few times to reduce the error. Either way, you need each call to the sharpsat oracle to have confidence that is 1 over n, because you're going to overall make n calls. Okay.
Could you use this trick with any oracles?
Excuse me?
Could you use this trick with any oracle? So if you have some language L which is in IP, then P to this language is also in IP?
Sure. Yeah, P to the IP is in IP because you can just run the IP protocol, right? I agree. But here, look, kind of we were starting with something that we didn't know had an interactive proof, right? P to the sharp P, and we're constructing one. If you start P to the IP and you're trying to connect it to IP, you're kind of some sort of kind of local connection about interactive proofs, right? But yes, I agree. P to the IP is in IP. And more generally, anything that is to an oracle and you can implement the oracle with an interactive proof, then you can put into basically lay it out as some big interactive proof. Great. So I think, yeah, that is my last slide about sharpsat. So what I'm going to do now, I'm going to stop the recording and answer further questions.